Hello and welcome to a new session. In this one, we are going to continue with our worked example, and we will be looking at today at running the analysis and finally visualizing the analysis results. So just to recap, we have already defined the geometry at the beginning, then we defined the materials, the sections, we assigned those to our structure, we defined the boundary conditions, constraints and restraints. Last time we defined and assigned the different loads to our structure, and basically today we are going to run the analysis. So let's go right ahead to in our control bar to the analyze option over here, and if you click on it, so there are a number of things, but for the purpose of this workshop, typically you would just need to go to run analysis over here, which you can execute by just clicking here, or maybe by using a shortcut F5, or even from the toolbar over here, you can just run it directly from there. But before we run the analysis, let me just show you something quickly, which is the first thing that we have here, which says set analysis options. So if you go ahead and click on this, so the analysis options, you see here that you have the 6 degrees of freedom for the general 3D model that we have discussed previously, and they are all selected over here. And here you have it says fast degrees of freedom, or DOF. So DOF is the abbreviation for degrees of freedom, and you have like some templates that you can select from. Of course, because when we built our model, we already selected a 3D space frame, so that's why right now all the degrees of freedom are selected, which is the space frame option. So what does this mean? This means that in your model all six degrees of freedom are active, and in the background, when you execute the analysis, in the background, SAP will build the stiffness matrices for the whole structure, and the size of this stiffness matrix will depend on the number of joints in your structure multiplied by the number of degrees of freedom, the available degrees of freedom at each joint. So if you multiply this by that, you get the size of the stiffness matrix, or which essentially how big is your problem that's going to be solved by the program. Now, of course, the lesser the number of joints in your model, and the lesser the number of degrees of freedom at each joint in your model, the faster the analysis would go. So, for instance, here we have the full 6 degrees of freedom, which is fine. But let's assume that in this structure that I'm doing some analysis for, I'm applying all the loads in the gravity direction, and maybe if you are considering like some lateral forces or wind or something, you are just considering these forces in the y direction, so something that pushes the structure laterally in the y, in the x-axis, like in this direction, in the global x-axis. So you might think, like, if this is the case, then this means that since my structure is regular, I'm doing a static analysis and my structure is regular, like the plan view, it's symmetric and it's regular. So you would assume that since you are applying just gravity and some lateral forces in the x direction, so my 3D structure will not or should not ideally deform or deflect in the y-axis direction, so in this direction. So if this is the case, then you can actually come here and you tell SAP that, you know what, I don't care about uy because there shouldn't be any deformation in the y direction. I'm assuming that. And then you can unselect this degree of freedom. Now, what's the benefit of doing that? Well, I'm just, in theory, and also practically, if you have a very large structure, like a high-rise building that's much, much bigger than this one that we are analyzing over here, when you remove some degrees of freedom, the stiffness matrix becomes smaller, and of course, to solve a smaller system of equations with a smaller matrices, it will become much faster. In our case here, it doesn't really matter because this is a very small model, and you will see that the analysis will take, well, less than 5 seconds, so it really doesn't matter. So I can just activate all degrees of freedom. But this is just to give you an idea what does this means and how can it be useful. Another thing, of course, let's also assume that when you started this model, you did like a 3D model, a 3D template, and after you build all this thing, you said, you know what, I don't want to analyze the whole structure. I just want to analyze the frame, just one frame, the planar frame in the XZ plane. Okay, so you said, okay, since I want to do that, so let me go ahead and delete all the other elements and just keep this perimeter planar moment frame in the XZ plane and delete everything else. And then you go ahead and do the analysis. You have to be careful here because so far all degrees of freedom are active, all right? But your frame is now a planar frame, a 2D frame pretty much. So this means that if there is any kind of force or instability in the out of plane direction, which would be the y direction in this case, your structure can be unstable. So let me show you what I mean. Okay, so look at this example that I'm displaying here. So again, this is, let's assume that this is the two, like after you drew the 3D frame, the entire thing that we just did, you said, you know what, I don't care about all these elements, I will just remove them, delete them, and just keep the planar moment frame, which accidentally has like some pinned connections in this direction, meaning that the frame is allowed to rotate about the x axis at the supports. So the problem here, if you set the analysis options, in the analysis options, you are activating all the degrees of freedom, what will happen is that SAP will build the entire stiffness matrix considering the displacements in the y direction and the rotation around x. And then analysis will start, and when you have some equilibrium the solution of the equilibrium equations is going on, you can get some small forces acting out of plane, like some small instabilities because of the accuracy of the solution. And any small instability that can act out of plane in the y direction will be pushing this structure like this. And since you already said that you have pinned connection in this case, so there is nothing stopping this frame from toppling over and falling, which means this will cause a numerical instability. So this means that your structure is unstable in this case. So you will have a problem if you run the analysis like this. So what do I mean? Okay, so what I mean, if you do something like this, you need to make sure that you activate the plane frame option, meaning I'm just modeling in the XZ plane, which in this case I'm modeling here in the XZ plane, that's it. And I don't care about anything happening out of plane in this direction. So by default, the rotation around X is now not activated. The displacement in the Y direction is not activated. Twisting, which is the rotation around Z, is also unactivated because this implies that there is movement out of plane. So automatically those will be deactivated, and this will make the analysis faster, and most importantly, you will not have any instability problem. Of course, in our space frame that we are doing right now, it's fine to have everything activated because in the Y direction, well, you already have a braced frame system, so you have something to carry any out of plane loads. So this is just quickly, what does this mean, and the available degrees of freedom. So it's very important to make sure that you already have the adequate degrees of freedom activated in your model. I will not go through other things like the solver options here. Those are things that you can check if you are interested in, like for parallel computing or things like that. But this is not important for our introduction workshop. So I will leave things as they are, space frame, all degrees of freedom activated, and I will click OK. Now that the analysis options are set, the next step would be to execute the analysis. So I will go here and click on Run Analysis. Typically, as I mentioned, I typically don't go to the control bar. I go to the toolbar directly and click on the play arrow or the Run Analysis arrow over here. So if I click Run Analysis, you will see here a list of all the load cases that we have defined. If you remember, we have defined a dead load case, a live everywhere, another load case, and a live on half of the structure. And there was the model analysis, which was by default defined in SAP. And here, the action that says here that we want to run all 4 cases, but the current status is not run, meaning we didn't run it yet. So basically, you need to go here and say run now. But maybe before we do that, the model analysis, we don't care about the model analysis in this case. We haven't defined any masses, and maybe we don't care about it for our specific example. So if this load case or any other load case you don't want to run it, you can just select it, and then you go here and you click on the Run, Do Not Run case. So if I click on it, now it says do not run. If I click again, now it's run, and so on. So I can deactivate this load case. I don't want to run it, and for the rest it's fine, let's run it. And then you can click on Run Now. So now the analysis is being executed, and that's it. As I mentioned, it took like around 5 seconds or less than that, well, depending on your PC and how big is your model, and automatically the analysis has been concluded. And you see here, it says right now in the title of your viewport, it says deformed shape dead load. So this is the deformed shape of the dead load case. Of course, the deformed shape is scaled in order to make the deformations and deflections observable. So this is automatically done. So I think here probably the scale factor is like something like 100 times more or something like that. We can modify this later on as I will show you. But anyway, so from the deformed shape, it's very good to observe the deformed shape to make sure that things make sense. So for instance here, yeah, things make sense. I can see the braces buckling, I can see the slab deflecting downward, and the slab is moving with the edge beams together. So I don't see any node that's moving by itself or a member that's flying or unstable or something like that. So looking at the deformed shape is very, very important to identify if you have any problems. Now another thing, if you notice here, the slab, now you can see all these small pieces in the slab. The slab is now meshed. So now you can see the mesh that we have conducted previously to the area element. So now you see if I remember correctly, we did like 12 by 10 elements when we did the mesh for each area element. So now you can see here the 12 by 10 mesh size. Okay, and you can play with that. As we said, you can make the mesh more coarse or more refined and see how will this affect the results. So here, since we did like 12 by 10, it seems like very adequate mesh, and everything, the deflections look smooth everywhere. You will notice also another thing, since now we are looking at the deformed shape. If I hover over any point in my model, I get some data. So if I hover here around this point, I get the point number at the top, and then I get the value of each degree of freedom, U1, U2, U3, rotation around 1, rotation around 2, rotation around 3, the values. So in this case, for instance, since we are looking at gravity loads, we care about the vertical deflection of the slab, because typically if you are designing the slab or designing the beam, you care about deflection because you have some serviceability limits in the design code that will tell you the deflection cannot exceed this much. So you care about the deflection. And the deflection in this case is the degree of freedom U3, which corresponds to the Z direction. So if I look at U3, it says negative 0.00, if you can see it, negative 0.0017. Of course, because we are using the units of meter. But when you are looking at deflections and in meter units, it's not very realistic when we are talking about structural deflection. So you can modify this by going over here and changing the unit. So instead of kilonewton meter, let's make it millimeter. And let me go again and hover around this point. So now it says negative 1.65 millimeter. So now you can check negative 1.65, it seems reasonable. You can check it with the limit in the code and see if this is acceptable or not. Alright, so you can do the same by moving at any point, like at the mid span of the slab. It says here 2.7. So again, things looks reasonable. Let's explore more. So how can we visualize other things like deformed shape for other load cases? So everything you can access from these three icons over here. So this is the display, which is pretty display toolbar or for visualization. So if I click on this one, this will show me the undeformed shape. If I click on the next icon, it says show deformed shape. So if I click on show deformed shape, I get all these options. So first you select the load case, so dead, live, live half, and the combinations that we defined. So you can select whatever you want. You can, for instance, click on live half. And then you have other options, just how the deformed shape will look. Wire shadow here, this means that it will show you the deformed. I think this will show you the undeformed shape, the deformed shape on top of the undeformed shape. The scaling, so now the scaling of the deflection is done automatically, but you can select user defined and you say, okay, scale it by 10, scale it by 100, depending on what you want. I typically leave it automatic, that's fine. And okay, and then you just go at the end and click OK. I think because here the resolution of my screen is a bit large, so let me modify the resolution just for me to be able to see the rest of the dialogue. Okay, so I changed the resolution, and now I will just again select live half and I click OK. So I think I was selecting this viewport. Let me select this viewport and show it here. So apply. Okay, so now you see, because this case is the live half, so we added on half of the building, so we see this part is deformed, the other part is not deformed. So that's it. These are for the deformation. So again, you can look into the different load cases and make sure what's happening. If you are checking deflections, for sure it might be important to look at the combination. Okay, like the combination envelope. Apply, okay, and then I can check the maximum deflections. So here it says negative 5.4 millimeter deflection in the slab. So this is the maximum envelope when I added the dead load and the live load together with the scaling factor. Let me show you something else as well. So you can play an animation of the deformation. Let me zoom a bit. Let me actually close this viewport now. I will just use one viewport, the 3D view. So I close this one. Okay. So if you go downward, it says here, once you have some deformed shape showing in your screen, you can go to the bottom right and it says here start animation. And if you click on it, so now it's loading. You can see it loading here. Once it finishes loading, it will start playing smoothly. So you can speed up the animation or slow down the animation from here. Then you have this characteristic sound by SAP that's playing in the background. Here from these arrows, you can actually alternate between, instead of accessing the different deformed shape for the different load cases from the icon over here, instead you can just go to these arrows and just go left and right to move between the different load cases. So this is for the deformations. Okay. The next thing that we will look at, Well, the second most important thing is, of course, the forces, the moments, the stresses, the reactions, all those things. So this, from this icon over here that says show forces / stresses, if you click on this one, again, so you have the different options: joints, frames, and shells. So depending what type of thing you want to show. So if you go to joints, for instance, again, you select which case are you looking for to visualize results. And then if you say, of course, since you are looking at joints, so the only thing that you can visualize for joints is pretty much the reaction forces, which, by the way, if you go here and you click apply, so now using arrows, which is what we selected here, you can see here the reaction forces values at each support. So for instance, at this support, I see a vertical force of 4,211. I think this is the moment. And you have the reaction in this direction, Rx 3.41 kilonewton. You can change again the units back to kilonewton meter. It's probably better since you are talking about forces. If the arrows are not, if you don't want to show it as an arrows, you can select tabulated form and you click apply. So now you get a list. So at this joint, I have F1 is equal to 0, which is in the x direction. F3, the vertical reaction, is 239.8 kilonewton. M1, the moment around the x-axis, is 5.52 kilonewton meter, and so on. Okay, so this is for the joints. You can visualize the reactions in this way. Let's look at something else. So let's go now to the frames. So for the frames, again, you select the case that you want to investigate. You select what do you want to show. You want to show forces or stresses. Well, in our case, since we have only line elements, we don't really care about stresses. Everything is elastic, so I will just want to look at the forces. Then you need to select what kind of force. So we have 6 degrees of freedom, so we have 6 forces, right? So we have axial force, we have shear about axis 2, shear about axis 3, torsion, moment around axis 2, and moment around axis 3. Okay, which depend, of course, on the cross-section local axis. Now, if you look at, let me illustrate to you what this means. If you have some generic cross-section, let's say your typical I section like this, like the ones that we defined, those sections actually, the axes are like this. So this is axis 3, and this is axis 2, and out of plane, which is in the longitudinal direction, this is axis 1. So this means that what we really care about is pretty much moment around axis 3, which is the strong axis moment. Okay. We also care about the weak axis moment, which is M2 in this case. All right. And we care about the shear force. So you have the shear force in axis 2 direction, V2, and you have the shear force in the axis 3 direction, V3. So if I go back, typically we look at the axial force, shear to 2, which is the shear in the vertical direction, and M33. Those are the most common or the main force components that we look at in our typical structure analysis. By the way, this axis thing that I discussed, like 1, 2, 3, you can actually, probably you have noticed this in the define when we went to the define frame sections, if you open any one, you can see here the axes. It says 3 and 2. So this is the 3 axis and this is the 2 axis, and the 1 is the one out of plane. All right. Okay. So now let me go again to frame shells. So let's look at the dead load. Let's start by looking at the moments, or let's go by let's start in sequence. So let's start by the axial force, and the visualization that we are going to do here is by field diagram. I'll show you what this means. So if I click apply, so now let me put this a little bit on the side. So now we see the axial force diagram pretty much in my model, and things make sense. I don't see any axial forces in the beam, which as you would expect. I see axial forces in the columns, and it starts small in the top story and then it gets bigger when you go to the first story. I see some axial forces, of course, in the braces, as you would expect, right? But if I hover on any column or any element, you can see that the force, you can read it at the bottom. So you can see here the force, while I'm hovering, I can see the force written like this. If you want to show it in another way, you can say show values, and you click apply, and now you will see the axial force diagram, and at the same time you will see the values of the axial force. You can look at this in the 3D view again. You can look into the, let's say, XZ view, something like this, which may be useful if you want to take some screenshots to put in a report or something like that. So this is how you do it. If you think the values or the values of the forces or something are a bit small, you cannot read the text very well, you can actually go to options, you can go to dimensions and tolerances, and you can change here the maximum graphic font size. So you can make this higher. So you can make this, for instance, instead of 8, 12, and instead of 3, you can make it 6. If you click OK, so you see now, so the text becomes bigger. So again, you can change those in order to make sure that you have a good screenshot that you can put in a report. Let me go back to the frame sections. Let me look at the shear force, shear 2-2. If I click apply, again, so now you see the shear force, and of course the shear force is mainly large shear forces in the beam, and you can see that the shear force here in the beam, it has like this step, like ladder increments, and these increments are based on the number of meshing or the divisions that we did in the beam, which is based on the meshing that we did in the area element. If you want a smoother or a more refined, like higher resolution shear force or moment diagram, then you can increase the number of mesh or the number of divisions along the beam. But this is fine for our analysis. It looks decent enough. So again, these are the shear forces. If I look at the moment 3-3, if I click apply, again, so you can double check this. Okay, things make sense. I can see here negative moment in the interior support because this is a continuous beam. So I see negative moment, and this is a fixed connection. I see some positive moment in the midspan, as you would expect. Let's look in the 3D view, and let's put the field diagram instead. Okay, again, things make sense. If I look into the, let's say, in the braced frame direction, so this is the YZ. So again, things make sense. I see that the moment is 0 at the end of the beams, which as we would expect, because we did moment release. If you remember, we did moment release at the end of those beams. So I shouldn't see any moment at the end. If you see a moment, then this means that you did something wrong with the moment release. And then you have some negative moment here because this is a continuous beam above the braces. The braces, of course, no moments at all, very small values, like negligible, but typically you don't see any moments in the braces. So again, looking at the field diagram, looking at the values, you can double check if everything makes sense, if positive moments, negative moments, axial forces, the general shape is as you would expect. If you see something wrong, then you can fix it, go back and fix it, and rerun the analysis again. So that's pretty much it. Again, you can look at different cases. You can look at the combination envelope, apply. So you see here for combination envelope, you see here that you get, let me look at XZ again. So you see here that you have two bending moment diagrams superimposed on each other, because combination envelope, if you remember, this combines two cases, combination 1 and combination 2, and it shows you the envelope. So pretty much for this beam, I see one bending moment diagram and another bending moment diagram from the other case. And if you are interested in the maximum, then you can just read it right here, what would be the maximum value. Okay. So that's why it's very useful to have the envelope combination. What else? Let me so if you want more details, let's say for instance, let's look again at the 3D. So you have this beam, and okay, you see things. You can, if you hover on the beam and you right click, if you do right click, then you will get this dialog box, which is you are basically probing in more details the values of the shear, the moment, and the deflection along the beam. So you can move here, click and move your mouse to the left and to the right, or you can just specify the location along the beam, and you can check the values of deflection, the values of moment, the values of the shear at any location through the beam. So this is very useful, and from here as well you can change the case, what you're looking for, the moments. You can select the location based on the relative distance from the edge of the beam or the absolute distance. So this is very useful if you want to get in more details about a specific element. So let me close that. So that's it for the pretty much for the visualization of frame element forces. The last thing that we are going to look at is the visualization of the shell forces. So if you click on shells, again a similar thing, you will need to select the load case or combination name. In this case, you can also go here to the component type. So what do you want to show, or what do you want to see? You want to look at forces, you want to look at stresses. So if you want to look at forces, so here again the same thing, M11, M22. So M11 and M22, these are the moments in your area element or in your slab. So this will be, if you have a two-way slab, so you have M11 in one direction and M22 in the other direction. And F11 and F22, those will be the axial forces in your slab in the 1-1 direction and in the 2-2 direction. Which is again, if I go here, if I have some kind of area element, something like this, I'm drawing in the 3D view. Please excuse my drawing skills. So you have some kind of area element like this. So again, you will have in one direction would be 1, x is 1, and the other one would be 2, and the one out of plane would be typically be 3. Okay, so that's why we are typically interested in the moments M2, which is called M22, and M11, which is the two moments in the two direction, or the corresponding axial forces. So again, you can look at those, like if I click M11 and I click apply and say OK, so you will get contours now, because this is a continuum, this is an area. So you have contours of the values. You may probably will need to look in the plan view, so XY direction, but let me see. So the XY direction, we need to go to the second floor or the third floor. So here I'm at the third floor, okay, in the XY direction, and you can see here, so this is the moment. You have some positive moment, as you would expect, at the mid-span, and you start as you are going through the near the beam here, you are getting some negative moments, because again this is a continuous slab. All right, I'm expecting also to see some moment in the 2-2 direction. If I click apply again, so you see here the same thing. So it's almost 0 at the edge, and then it goes positive, and then it goes 0 again. So this is the 2-2 direction. Okay, and this makes sense because my slabs here are two-way slabs. They are almost square, their aspect ratio, so it's a two-way slab. So that's why you are getting significant moment in both directions. So you will need those moments, of course, when you are trying to design for reinforcement, for instance, and things like that. Again, you can look also at the forces, the normal forces, if you are interested in those. Again, so it's almost constant. But typically, since we are looking at slabs for the purpose of this workshop, we typically are interested just in M11 and M22. If you don't want to look at forces, like moments, and you just want to look at stresses, so you can click on stresses, and you can look at S11, S22. So these are the normal stresses. Okay, the normal stresses in your slab. If you want to look at that, that's fine, and you can compare it with the maximum, for instance, compressive resistance of your concrete and things like this. So that's it for the shell. There are other things like shell strains, layer stresses, concrete design, but for by the way, so here for the shell stresses, you can normalize the stresses by the material strengths. So if you click apply, you can see here the values normalized by the FC prime, or the concrete resistance. So you can see, for instance, these blue values, the maximum values here are around how much? This is about -135, but this is 10 to the power -3, so it's about 0.1 or about 10% of FC prime. So you're far away from your compressive strength, which is fine. So then this is a good check, because you can check if something, because if you find here that you are like 5 times more than FC prime, then this means there's something wrong in the material property or in the loads that you defined. Concrete design, we don't care about that. This is, again, as we said, SAP can do design, but this is something for you if you want to check later on. You can check with other online tutorials or with the manual. We don't care about strains as well, at least for this case, but again, you can explore those if you want. That's pretty much it for the visualization of the results. Now the next thing, like knowing these results, it's very good to visualize the results. Okay, you can see it, you can take some screenshots, and you can put the screenshots in a report or something to present to your advisor or your boss in work. But it's not very practical, especially if you have like a big structure, you have many elements, many load cases. So you want this to be done in a tabulated way. So you need to export the data, for instance, in a table to an Excel sheet or something like that, where you can process later on and do specific things with the data. So how can you do that? In order to export the data, what you need to do is you go to display, you go to show tables over here, you click on that. So here it says choose tables to display. So you can pretty much, you will get some information. So you can select any of those checkboxes. So for instance, if you want a report on the load pattern definitions, so you can select this, for instance. Okay, if you want you want to look at the frame assignments, the sections and these things, so you can select this checkbox, and so on. So you can, all the data that we defined, you can select those here in order to get a report out of it. All right. Now, let's just focus on the analysis results. And let's say that you are interested in the element output. So if I go, let's not select everything. From the element output, I'm interested in the frame output. And I want the element forces. I don't want the stresses. I don't want the joint forces. I just want the element forces. So I select element forces. You can go here and you can select specific load cases to show in this table that you will get. So you can just show the combination, the forces based on the combination cases, or maybe you want to select everything. This is up to you. Let's say that you just care for combination 1, combination 2, and the combination envelope, the combination cases. So I'll just leave those selected. So that's it. The next thing that you need to say, just say OK. If you click OK, automatically a table will be generated, as you see here. And it says here element, forces, frames. If we have selected several options from the previous selection tree that we had, then you will get more items in this drop-down menu. But right now we have only selected element forces of the frames. So you can see here the frame ID, the frame element ID. You can see the location. You can see the location along this element, like at 2 meter or at 4 meter. You can see the name of the load case, combination 1, and then you can see the forces P, shear, shear 2, shear 3, torsion, moment, and so on. Now, of course, this might be a bit too much information. I mean, if you look here, this is a very huge table for all the elements, and you're giving me the values at all locations, and I don't really care about torsion. So how can you do that? So let's say filter it. So you go to filter, format, filter, sort, and you go to Format Table. And here you can see all the fields that you see in your table. And next to each one it says printed. But for instance, if I don't care about the torsion, so you can just go to the torsion and double click on the where it says printed, and now it says not printed, so it will not show. I don't care about shear in the three direction. Double click on that, you remove it. I don't care about the moment in the y-axis, for instance. I'm just saying that if I don't care about that, then you can click and you say not printed. I don't care about the frame element ID. I don't care about the element station, so I can say that. What else? Step type text, we can remove this as well. The case type, like is it a combination or is it an actual load case? Maybe this is not important, so we can remove that. You can also modify the units of each field. Okay, sorry, the width of each part of the column. So you can modify this, and then you can say you can also click on sort. So you can sort the data based on the frame element number, or you can sort this table based on the load case, okay, the load case name, or you can sort it based on the maximum, like M3, like what would be the maximum moment in your model will be shown at the beginning. So you can play with this if you want, and you can click, after you're done, click OK. So now, as you see, now it becomes much shorter table. After you're done, and now that you have your table ready, you just need to go to, if you want to export it, to use it in Excel or something. In most cases, people would typically have like some kind of an Excel macro written, or like a pre-formatted Excel sheet that you just import the data. If you are working with SAP a lot, you just import the data to SAP and then you execute this macro or use this pre-formatted Excel sheet to automatically extract the specific information that you want. So if you go to File, you can go to Export Current Table, and then you can click to Excel. So if I do that, so automatically the table has been exported to Excel. Now again, as if I have some kind of macro written in Excel, or manipulate this data and extract specific values for moment and shear and so on, and use them automatically in some kind of a design scheme that you have. So this is, like, in a nutshell, again, like this is how can you export information to Excel. Again, there are many things that you can print out. We just printed like element output, but you can, as we mentioned, you can get more information regarding the frame assignment, the area, the system data, the property definition, all the things that you have done. You can click on those, like the material properties. You can select this and you can say OK. Then you will get a list, a summary of all the materials that we defined in our model, and you will get like the basic description for each one of those, and you can export this again to Excel or later on to Word or something like that in order to make some kind of report. So this covers today's session, visualization and exporting of data. And that's it. So thank you for listening, and you can explore more. Of course, we are just going through the basic things just to get you familiar with the different options and functionalities in SAP. But of course, there are many things that you can play with. So this is up to you to explore more. So thank you very much for your attention.